Okay, thanks, Paul, for the introduction. So good morning, everyone. I'm Lorenzo. I work at Qilimanjaro as a measurement engineer. And today I'm going to talk about Fluxonium qubits for analog quantum computation. And so first of all, if you want to perform coherent analog quantum computing, very generally speaking, we need to be able to implement an Hamiltonian like that one, which contains both longitudinal and transverse term in some single qubit basis, plus also ZZ coupling terms and XX coupling terms. And furthermore, this coefficient A, B, C, and D, in general, they need to be time dependent, and we need to be able to tune them. They also need to be quite similar to each other in magnitude. And also, we want to be able to switch them off whenever is needed. So you can imagine that combining all these features together is quite a difficult challenge. And people are trying to solve this problem using a bunch of different hardware platforms. And this is just a non-exhaustive slides summarizing a few of those. So we heard also throughout this conference the possibility of using natural atoms on one hand. People are also trying to use dopant-based quantum dots, and of course also superconducting circuits, which is what we are also doing at Qilimanjaro. And in particular today, I want to show why we want to use superconducting qubits, and in particular why at Qilimanjaro we are interested in using Fluxonium, and I would like to show you that Fluxonium is good because it can be naturally mapped into an analog quantum coherent Hamiltonian. So this brings me to the outline of my talk. So in the first part, I will show you how we can map a Fluxonium superconducting circuit to a spin particle. In the second part, I will describe our Fluxonium prototype together with some experimental results. And finally, I will give some conclusions. So let's start. So before going to Fluxonium, let's just review quickly what an LC oscillator is. So an LC oscillator is essentially a parallel circuit between involving a capacitor with a charging energy EC and an inductor with an inducting energy EL, and where essentially energy can oscillate back and forth between the capacitor and the inductor. So this behavior is captured by this Hamiltonian which contain a kinetic energy part proportional to the charging energy, and a potential energy part which is proportional to the inductive energy and is purely parabolic in the superconducting phase. So so these are the definitions. So if you now quantize this harmonic oscillator, you end up again with this parabolic potential populated with a series of equally spaced energy levels, and the energy separation between these energy levels is actually the resonator frequency. So then a Fluxonium, we can see the Fluxonium as an LC circuit plus a nonlinear element, and this nonlinear element is provided by a Josephson junction, which is this cross in the circuit. And so the Hamiltonian now, it's basically the same as the one for a standard LC oscillator, but on top of that, in the potential energy term, we also have a nonlinear term, which is proportional to the Josephson energy times this cosine term in the superconducting phase variable. And furthermore, so we can play with external flux. I will go through into more details about this later, so that we can shift the relative position of this cosine term with respect to this parabola. So, and for this reason, we can actually achieve a series of different scenarios. So in this case, I'm giving you some example in the case in which the ratio between the Josephson energy and inductive energy is roughly about 10. So in the case in which we don't apply any external flux, so this is the potential that we get. So it's almost, well, it's a weakly anharmonic system. So also in this case, you have a series of almost equally spaced energy levels, and in particular for this particular case, well, the energy difference between the first and the second excited state is roughly 5 gigahertz, and the nonlinearity is on the order of a few hundreds of megahertz. So this is what is called the Transmon regime, because it's very similar to what happened to the energy configuration of standard Transmon. But this is not the regime we are interested in. So we are interested in the regime in which the external flux is equal to half flux quantum, in which, in this case, actually, the potential energy has this peculiar double well line shape. So let's see what happened around, so this point, so when the external flux is equal to half flux quantum is called degeneracy. And so in order to understand what happened around degeneracy, I just remind you that whenever we confine electrons in a superconductor, well, they are generically described by a microscopic state, which has this wave function here, and which has an amplitude term times this phase term. And whenever you constrain such a microscopic state in a superconducting loop, as represented there in the circuit, this phase must be single valued. So it means that in order to, if you constrain this state in this loop, it must satisfy what we call a flux quantization, which says that the superconducting loop phase must be a multiple of 2 pi. So you can imagine now that at degeneracy, these peculiar boundary conditions are satisfied by 2 opposite circulated currents, and this is what we call persistent currents, plus minus IP, which they both act either to expel the external flux or to pull additional flux into the circuit in order to satisfy this boundary condition. So now the trick is to essentially represent these 2 opposite circulating currents as a spin-up and spin-down particle, each one localized in a minimum of this double well potential, which is so each of these spin-down, and spin-up states is well described by well-localized wave function within each well. So this is called the persistent current basis. But of course, you see also, as you can see in this potential, these 2 states are coupled together by this tunnel, by this barrier, because the barrier is not infinitely large. So you have a finite tunnel rate, which is typically labeled delta. And delta, this tunnel rate, is proportional to the ratio between the Josephson energy and inductive energy. So this means, and this tunneling, of course, couple the spin-up and spin-down states. So in this regime, the Hamiltonian, it's purely transverse in the persistent current basis, so it's delta times sigma x. And the eigenstate are symmetric and antisymmetric linear combination of spin-up and spin-down states. And the energy separation between these 2 states is called the energy gap and is indeed given by delta. So one important thing that is that, as you might have already understood, is that because the 2 opposite circulating currents have equal weight in this eigenstate, the net current flowing through the qubit is actually 0. And one thing I want to point out is that so far we have seen that Fluxonium contain only a single Josephson junction, but if we actually change the single Josephson junction to a squid loop, you can, well, essentially the squid loop, roughly speaking, is equivalent in having a single Josephson junction, but with a tunable Josephson energy. And this tunability is given by this cosine term here in the phi squid variable. So essentially you can, so this is important because it means that by tuning an additional external flux, so this phi squid variable, you can actually tune the tunneling rate between the 2 well, and so you can tune the energy gap. Okay, so far we've seen what happened at degeneracy when the Hamiltonian is purely transverse in the persistent current basis. So, but what happened if we move slightly away from degeneracy? So, for example, we apply an external flux equal to 0.4 phi naught. And so in this case, you can see that we also tilt this double well potential by an amount epsilon. So this means that now the eigenstates start to be more localized in one well or the other, meaning that this energy eigenstates contains a finite amount of current in them, and so that the actual Hamiltonian, it's not only transverse but contains also the longitudinal term, which is proportional to this epsilon, so to the tilting of this potential. So a nice way, an intuitive way to see, to look at this is to essentially define a current operator with this expression, and basically so that it points in one particular fixed direction, which is called zeta prime here, and look at epsilon and delta like the components of the magnetic field B, so that by tuning delta or epsilon or both, you can actually tune the direction of the magnetic field, and so meaning that you can tune the direction of the energy quantization axis with respect to the current operator. And importantly now epsilon equal to 0, so where you have no tilt, the current is purely perpendicular to the energy quantization axis. So this means that if you have current fluctuation, those, at least at degeneracy, they do not transduce into energy. So this means that Fluxonium actually at degeneracy is flux insensitive. And this has led to extremely long coherence time with Fluxonium, and people have shown coherence times at degeneracy up to millisecond. Okay, so now what happened when you couple two Fluxonium together? So in a very simple configuration, you can imagine to couple that inductively by some mutual inductance M, so that a current in one of these loop can induce another current in the loop of the second qubit, so that the coupling terms you can write as M times I1 times I2, and if you use the previous expression for the current operator, you end up with a coupling Hamiltonian which contains both XX terms and ZZ coupling terms, and XZ coupling terms. So if we now put everything together, the total Hamiltonian for a Fluxonium qubit, it's contains transverse and longitudinal terms in the persistent current basis, as well as all these coupling terms above in this coupling Hamiltonian. And if you now recall the initial analog quantum computing Hamiltonian that I showed at the beginning, you can see that actually there's quite they're quite similar. And furthermore, these coefficient ABCDs that we have, we can actually tune them with flux, so using tunable flux, and we can also make them time dependent using flux pulses. So this is all very good, but of course we have some challenges. We have some open question, and for example, how can you make an interaction term dominant over the other in an arbitrary way? And so we heard about it a little bit from Andrea on her talk on Monday. So this is not so trivial to do. And also, how can you tune an interaction term to 0 also in an arbitrary way? So these are open challenges that we are currently working on. But with this, I'd like to start to go through the second part of the talk, which is about our Fluxonium prototype, because so far I mainly showed you circuits where essentially capacitor and inductors are generally given by the circuit elements, but in real life actually capacitance and inductor are distributed all over the plane on a chip. So this is on the left, you see an image, an SEM image of one of our first prototype. So the base layer that we use in this device is a thin film of aluminum. The thickness is about a few hundred nanometer thick. So, and what you see here, well, this large highlighted part is the ground plane of the circuit. Then in the middle we have the squid loop, where essentially for the junction we use standard aluminum oxide tunnel junctions. You also see here in yellow the external loop, and where the inductance is provided by a Josephson junction chain. And these big plates here corresponds to the capacitors of the Fluxonium. And what we see, in addition to all these parts, are also flux lines that we use for biasing for biasing the loop, so to apply external flux. So these these flux lines are essentially mutually coupled to the corresponding loop. And so what we need to do in order to apply external flux is to apply some voltage, traducing it to a current via resistor, and then via this mutual inductance we can actually induce an external flux in the loop where we want to apply it. Okay. So the first things we do when we want to test one of our devices is to actually probe the two-dimensional periodic potential of the Fluxonium, which I also report here as a reminder, and where essentially, we have this, the potential can be taken proportional to these two cosine terms, one cosine terms in the external variable and other oscillating term in the squid variable. So here we plot the signal as a function of the external voltage on the x-axis and the squid voltage on the y-axis. And so you can see that we clearly identify this two-dimensional periodicity of the potential, but you also see that these periodic pattern are not aligned with the Cartesian axis, or to the direction which we apply the voltages. And that's because of crosstalk. So it means that these mutual inductance that I described before, they're not simple number, but it's actually more of a matrix. So that essentially when we apply, for example, flux on the external loop, we don't only apply flux on the external loop, but we also have some crosstalk from the external loop to the squid loop, and vice versa. So what we need to do then in order to compensate for this is to find the direction of this periodicity so that we can implement a sort of a change of basis in order that we can align our sources to the direction of the potential of the Fluxonium. So in this case, for example, it's a calibrated data, and you can see that we calibrated now in the external flux and in the squid flux, and the periodicity it's well aligned with the Cartesian axis. So you can imagine that, of course, I'm showing you the results now from a single planar devices, but when you think about scaling this processor, actually minimizing crosstalk, it's really important, and it's also something that we are currently working on. And the next things I want to show you is some qubit spectroscopy data. So this is a signal as a function of the external flux on the x-axis and the drive frequency that we use to drive qubit transition on the y-axis. And on top, you see also the line shape of the potential, and on the left, on the right, corresponds to the line shape of the potential at the extremes of the x-axis, and in the middle at the degeneracy. So, and this is for a particular value of flux applied to the squid loop, which is equal to 0.4 phi naught. So we can identify mainly 3 lines. The more visible is the F10, the fundamental transition, and F20. But we also see very, very weakly the F21 transition. And on the right, you see, we extract the peak, or actually the dip, I should say. And of this, no, actually it's a peak here. And then we can fit using a global fitting, and so 3 parameters to fit all of this line. And here I report the fit parameters. So EJ, the Josephson energy is about 15 gigahertz, charging energy about 500 megahertz, and inductive energy of about 3 gigahertz. And here I show basically other spectroscopy data but with a slightly different value of the squid flux, meaning it's a slightly larger tunnel barrier. And so you can see that in this case we can also identify the F10 transition, the F21 and F20, together with a bunch of other lines that we know where they come from, but I won't comment about. And we can fit using exactly the same parameters as in the previous slide, and you can see that they match pretty well. But importantly, I want to point out that the fundamental transition, in this case, it can reach value transition energies of which is smaller than 100 megahertz. So it's really a low frequency, and this is also another good thing about Fluxonium because it makes it less susceptible to dielectric noise. So in conclusion, I hope I show you that Fluxonium, it's an ideal platform for realizing analog quantum computing because it can be naturally mapped into a spin model and can realize different spin-spin interactions. It's also insensitive to flux noise, and this can lead to extremely long coherence times. I show you our Fluxonium prototype, in particular discuss the planar design that we use, the crosstalk compensation, and also that Fluxonium can work a really low frequency, which is good to minimize effect of dielectric noise. But of course, I show you mainly the good properties, but of course Fluxonium also has challenges, and for example, well, how can we read out the persistent currents of the qubit? This is something that I didn't cover throughout the talk, but Victor will discuss about this in the next talk. How can we achieve tunable interaction? Well, we heard it from Andrea on Monday, and it's still something that we need to measure and to work on. And finally, how can we scale up? I mentioned also that it's important to minimize crosstalk when we want to scale up. And I want to mention that at Qilimanjaro, we are also working in developing a flip chip architecture where essentially we separate the qubit chip from the control chip, where the qubit chip contains only the Fluxoniums, while the control chip contains all the superconducting lines that we need in order to control the qubit. And then essentially we can flip one chip on top of each other so that we can achieve sort of inductive coupling between the two and capacitive coupling between the two, and we can operate it in a standard manner. And very recently, we started to measure one of the first flip chip prototype containing 15 qubits, and we measure 15 out of 15 qubit working, which is really good news. So, well, stay tuned for additional results on this. And with a nice picture of our team, which is probably already not up to date, thank you all very much for the attention.
Good. We have time for some questions. Yeah, Johan's question here. On, I think. Oh, yeah.
So, hi. Yeah, very nice. Maybe this is more of a remark than a question. So it's about the flux noise insensitivity. That is correct for global flux noise. But when you have two loops, right, when you have the Fluxonium loop and the squid loop, actually, even at the sweet spot, you are still susceptible to local flux noise. Okay. Now, the unfortunate surprise of nature is that flux noise is very local, actually. The dominant flux noise is local. So you will pay a price in coherence if you have more than one loop in a Fluxonium.
Yeah. Indeed, I mean, actually, it would match also with what we've seen when we measure coherence on single-loop devices and on double-loop devices, and we could see that, yeah, there is kind of a gain in having a single loop.
Excellent. Speaking of that, can you tell us more about the coherence times that you have measured?
Yeah. So at the moment, well, I discussed about the possibility of reaching up to millisecond. I mean, very long coherence time. But at the moment, we are not there yet. Reason, well, there could be different reason for it. Not sure how much I can say about it, to be fair. But yeah, I believe, at least personally, I believe that most of the improvement that we can do at the moment is related to fabrication imperfection, rather than design or setup related aspects. So, and yeah, that's I think it's the only comment I feel I can make at this point.
Good, thank you.
Time for maybe one more quick question. Matthias, yeah.
Thank you. It's very basic question from a theorist, but how do you how are the Josephson junction arrays different from? Is it like actually just a chain of individual Josephson junctions, or are they different in terms of manufacturing?
No, I mean I think it's just. I mean, I'm not now sure exactly how the chain are fabricated. If the question if they're fabricated in the same way as single junction.
Yeah, basically, just do multiple times single ones, or
probably not exactly the same fab. Let's say the same evaporation process, but the principle is the same. You just put a series of Josephson junctions, one after each other.
Slightly different.
Structure is different.
Yeah.
Okay. Yeah, I'll ask you later. Okay.
Good. We should probably move on to the next presentation. So let's thank Lorenzo once again. Thank you very much.